So just like we did with the growth model, right, we kind of want to have an idea, what do I expect something like f of x equals, 10 to the negative x to look like? Or f of x equals to 5 to the negative x, right? What do I expect that to look like? F of x equals, let's get another fraction in there, like, 6 over 5 to the negative x. And as we saw, what seems to be happening with all these functions, even though we're changing the base, right, that negative x is causing two things to happen. One, the one commonality is that we're going through 0, 1, right? That happened with all those graphs, right? As x goes to negative infinity, right, the function values on this way started going to positive infinity, and then as x goes to positive infinity, the function values kept getting closer and closer and closer to 0. So that was a classic exponential decay model that we saw 4 different times with our functions. And what would I expect 10 to the negative x to behave the same way, 5 to the negative x, 6 to the 5th to the negative x, right? These are all exponential decay models that have all these behaviors. So what can we tell about an exponential decay model? Well, first of all, the domain, just like the growth model, is everything. You can plug any value of x into the model and you're going to get an output. The range, well, just like the growth model, it's from 0 to infinity. It never touches 0, right? It's always above the x-axis, but it's definitely going to positive infinity. So we got that behavior. In terms of intercepts, it does have a y-intercept at 0, 1. In terms of x-intercepts, it doesn't have any, right? Because it's never a basic graph is never crossing the x-axis. Okay, and then what we also have is the end behavior, if you would. Let me address that. So as x goes to positive infinity, our function is going to 0. So it behaves like a horizontal asymptote in one direction, right? So the x-axis again is a horizontal asymptote, y equals to 0, but just in this direction. As x goes to negative infinity, our function values are getting bigger and bigger and bigger with it. They're going to positive infinity. So there's our end behavior of a exponential decay model. And then, of course, where the growth model was always on its way up, this one, right, starts down. If we move left to right, it starts going down very sharply, and then slowly, it's still decreasing, but at a very, very, very slow rate. So it's decreasing at a decreasing rate, if you would. And so we basically have that this function throughout the whole domain is decreasing at all times. It's always on its way down. It's quite sharply, and then it starts to shave off a little bit. So because it's always decreasing, that also means that this has no extrema, right? There's no local max or min. There's no absolute max or min, because we never reached a high point or a low point. An absolute value, we never assume a highest value, and we never assume a lowest value. So there's no extrema whatsoever. And then this is also, right, in terms of the even and odd function argument, this is not even and it's not odd, because it's not symmetric with the y-axis and it's not symmetric with the origin. So there's no even or oddness with regard to this function. All right, so there's our two models together, right? We have a growth model where, again, in both cases, a is greater than 1, right? But what's different, in a growth model, the x power is positive, and in a decay model, that x power is negative, right? So that's the biggest way that I can tell whether something's a growth model or a decay model. Of course, another way is to look at its graph, right? If it behaves like this is an exponential growth model. If it behaves like this, it's an exponential decay model. In terms of applications, let me just give you an idea of what we're going to see in the future. One classic application is when we have basically a famous one is radioactive elements, right? Because what we're saying here is if I have a lot of the element, the rate of decay is very, very sharp. But as my element starts to disappear, the rate of decay of the element starts to shallow out. So the more stuff I have, the greater the decay. The less material I have, the less the decay. Probably another one that makes more accuracy to you guys is the temperature in a room. Classic situation is, when we're drinking our coffee, if you guys are coffee drinkers or tea drinkers, it probably starts off very, very hot. The temperature is very high. But if I put it in a room that's, let's say, freezing, right, the temperature of the coffee is going to drop very, very fast. But as it gets closer and closer to the room temperature, right, freezing or zero, whatever, right, eventually the temperature decrease in temperature is going to start to taper off as it slowly gets closer and closer to the room temperature. Eventually it'll get so close to it, it'll be negligible, right? Because these function values are getting closer and closer and closer. So radioactive decay models, temperature models, we'll talk about those in the near future, but there's probably some other ones that will come up, but those are the big ones off the top of my head that I've seen quite frequently. All right, so there's our two models. Now that we know their basic shapes, just like we did with our basic shapes before, right, now what we can do is take those basic shapes and we can shift them up, we can shift them right, we can shift them left, we can shift them down, we can stretch them, we can compress them, we can do all kinds of stuff with them. And that's pretty much what we're going to do in our next video. So I'll see you guys then.